All right. What I want to do today is I want to talk about uh, structures that have double bonds and how you know where to put them. A lot of times you get structures where you have choices. And so let's take a look at one. Let's take a look at one that looks like this, CH2O. Okay. Now, if we have CH2O, we know that it has 4 plus 2 times 1 plus 6 valence electrons, right? Right? Because carbon has 4, hydrogen has 1, but there are 2 of them, and then oxygen has 6. So that's equal to 6 plus 6 is 12 electrons. Okay. Now, we can draw a skeleton like this. We can draw H dash C dash O, and then we have another H to put on there, and we can put the H either here, or we can put the H here. Either one is a perfectly viable skeleton, right? But we have to put C and O in the middle because hydrogen can only take one bond, and then it's full. Okay. Now, a question would be how you decide where to put it, but we'll get to that in just a second. First, let's fill in octets because it seems crazy to leave it all unfilled like this. So let's put top and bottom here, so 2, 4, 6, 8, and then top and bottom here, 2, 4, 6, 8, and now we have a skeleton. And then the same thing over here, we have top, left, and right, so we need 2 on the bottom, and then we need top, bottom, and right over here. So now we have our 2 possible skeletons. Okay. Both of these structures have the same number of electrons because they have the same number of atoms and they have only single bonds. If we count 2, 4, 6, 8, 10, 12, 14, this is 14 electrons. And we can count this one as well, 2, 4, 6, 8, 10, 12, 14 electrons. So you can see that it's 14 no matter which way it's arranged. At this point, we should compare 14 to 12, and we say 14 minus 12 electrons that we actually have means that there are 2 electrons too many, and that means we're going to need to add a bond. Okay, or an unsaturation, we say, right? So we're going to add 1 bond, and so our choices for our final structure are this. Or, again, we can't put the double bond to the H because H can only take 1 bond because it's in the first energy level, so it can only hold a maximum of 2 electrons. When we fill out our octets, this has 2, 4, so we need 4 more on it, 2, 4, 6, 8. The carbon, 2, 4, 6, 8 is already full, and so it is done, okay? If we go over here, 2, 4, 6, we need 2 more on the carbon. 2, 4, 6, we need 2 more on the oxygen. And now this structure is done. So how do we tell which structure is better? Or maybe they're both equally good. Well, what I want to think about is something that's in your notes. I want to think about how atoms fill out their valence shell. So if you look at carbon, carbon has, right, it has 4 valence electrons to start with, right? It needs 4 more valence electrons because 4 plus 4 would be our octet, right? It needs 4 valence, let's actually, instead of calling it valence both times, let's call it extra electrons. How about that? It needs 4 extra electrons. And so what it's going to do, it's going to form 4 bonds typically. And I say typically because it doesn't always. Sometimes it's going to form 3. Sometimes it will form 2. It depends on the structure, right? So it's going to form 4 bonds typically, right? Oxygen has 6 valence electrons. It needs 2 extra electrons. And so it's going to form 2 bonds. Again, typically. Okay. So which of these structures follows those rules? Well, this one, both of them have 3 bonds, right? 3 and 3. Well, that means that this carbon has too many bonds, and this oxygen has too few bonds, and this oxygen has too many bonds. Okay. Over here, this carbon has 4 bonds, and this oxygen has 2 bonds. This is a better structure because it follows the sharing rules that we set up here. Now, these are really just ways of remembering it, but here's a justification for these rules. If carbon has 4 bonds on it, right, like this, you can think of this carbon as having, looking more like this. Let's put these bonds as dots, right? And you can think of this carbon as having 4 electrons directly on it, right? In other words, 4 electrons directly on carbon, right? And that matches the 4 valence electrons it started with. And so this is ideal, and it means that carbon is neither more positive nor more negative than it would be if it were just an atom. Okay, but let's take a look instead at carbon with 3 bonds. If we draw this one, now we have carbon that looks something like this. And when we draw our circle around it, right, just in the immediate orbit of carbon, now carbon has 5 electrons directly on carbon. And that is 1 more than it normally has. In other words, 1, 2, many. And so adding having too few bonds means that carbon is effectively holding more electrons than it ordinarily would. In other words, the electrons are stretched less than they would be if carbon formed 4 bonds. So more of the electrons are sitting on carbon, and it ends up being negative. And what we do is we give this what's called a formal negative charge. Okay? So what I really want to stress right now is that when you're drawing these structures, we can figure out how many bonds an atom typically has if an atom forms more bonds than predicted by filling its valence shell. Right? For example, Cl, right, has 7 valence electrons. And so we expect 1 bond. Right? We expect 1 bond. So Cl with, say, 3 bonds, right, would have 2 more bonds than predicted. Well, if that happens, that is essentially pulling electrons away from the atom, and the atom then becomes more positive. Okay, the atom has a formal positive charge. We can actually calculate this if we want to using an equation that says the formal charge is equal to the valence electrons minus the sum of the unshared electrons right, plus 1/2 of the shared electrons. Right? So if we look at something like this, like chlorine with 3 bonds on it, right, but still having a full octet, right, something like this, should something like this form, right, then you would have chlorine with 3 bonds and 2 extra electrons on it. So we would calculate this, its formal charge, as being 7 valence electrons, right, minus 2 unshared electrons, plus 1/2 of 6 shared electrons. Okay. If we look at it this way, right, there are 1, 2, 3, 4, 5, 6 shared electrons, 2 unshared electrons, and chlorine normally has 7. So that becomes 7 minus 2 plus 3, which is 5, right, which is equal to positive 2. Okay. And so we would treat this chlorine as if it had a positive 2 charge on it, right? We could also do this by saying chlorine effectively has this layout for electrons, right? If we draw a circle halfway through the bonds, but all the way around the unshared electrons, you see chlorine has 5 electrons directly on it, and 7 minus 5 is a positive 2. So effectively, we've stretched electrons away from chlorine when chlorine usually has 7 electrons directly on it. Okay. All right. What about if an atom has less bonds than predicted, right? If an atom forms fewer bonds than predicted, right? If it forms fewer. For example, if carbon formed 3 bonds, for example, if we had something like this, right? Or if oxygen formed 1 bond, right? We had something like this, right? Then, the atom has a formal negative charge. Right? Because now the electrons are less pulled off of the atom, and so more of the electrons sit on the atom. So for example, carbon usually looks something like this, with 4 bonds on it. Carbon usually has 4 electrons directly on it. But if carbon looks like this, as it does up here, then when we draw a circle around it, now it has 1 extra electron. Right? And that would mean that we would assign a formal negative charge. So when we draw something like this, we put a negative sign on it, okay? And we can calculate that using that same equation. So if we say valence electrons minus unshared electrons, unshared electrons plus 1/2 shared electrons. Right? For this carbon, it becomes 4 valence electrons minus 2 unshared electrons plus 1/2, 2, 4, 6 shared electrons. If we look at this, that becomes 4 minus 2 plus 3 is 5, which is equal to a -1 charge. And so we put that -1 charge up there. So formal charge is a way of assessing whether an atom has more bonds than usual or fewer bonds than usual, and whether the electrons are distributed farther from the atom than normal or closer to the atom than normal. So if we take a look at just a regular structure of some sort, for example, we could have, well, let's try ClO3 minus, okay? ClO3 minus is chloride ion. Right? If we do this, chlorine has 7, oxygen has 6, so 7 plus 3 times 6 plus 1 for the negative charge, right, for the minus, the 3 oxygens, and the chlorine, right, for a total of 18 plus 7 is 25 plus 1 is 26 electrons. Okay. If we draw our skeleton, we have Cl. We draw our 3 oxygens around the outside. We draw our octets. Right, and here's our skeleton. If we count electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26 electrons, and so we know that we are done because we have the right number of electrons and we have full octets. So this is our structure, but let's look at the formal charge. If we look at this oxygen has 1 bond. We know, right, instead of the normal 2. That means that there are more electrons on the oxygen than it would be normally, and we know that that is going to give it a formal negative charge. Okay? If I wanted to, right, by only having 1 bond instead of 2, we're putting more electrons on the oxygen, and so it is negative. But we can also calculate that by saying 6 valence electrons minus 2, 4, 6 unshared electrons plus 1/2 of the 2 shared electrons. And then it becomes 6 minus 7, which is equal to -1, which is what we predict. Well, since these 2 oxygens are the same, then we can put a negative charge here and here. This chlorine, however, we can look at and we see that it has 3 bonds, right, instead of 1. Right, because chlorine with 7 valence electrons typically only forms 1 bond. Well, 3 bonds instead of 1 means the electrons are pulled farther from it. And so we're going to assume that that would cause a +2 charge. Okay, +2. Why +2? Because it's 2 more bonds than normal, right? So you've pulled 2 extra electrons away from the chlorine. Okay, so I predict +2 based on this difference. However, we can also test it. 7 valence electrons for chlorine minus, let's see, 2 unshared electrons, right, plus 1/2 of 2, 4, 6 shared electrons. And if we do that, 2 plus 3 is 5, and so we get 7 minus 5, which is equal to +2. And so you see this works. So formal charge is a way of assessing whether an atom has more bonds than usual, and if that means that the electrons are pulled farther from it than normal or pushed farther onto it than normal. Now, if we look at this, one kind of cool thing about this is that we have 3 negative charges and a positive 2. So we have 3 times -1 for the formal charge plus a positive 2 for the formal charge for chlorine, right? Chlorine and 3 oxygens, right? And if we do this, we see 3 times -1 is -3 plus positive 2 is -1 overall. And that's good because overall we know we have ClO3 with a minus charge. And so we see that the sum of the formal charges is equal to the charge on the ion or molecule. Okay. So formal charge is a way of assessing how the electrons are distributed within a molecule or ion. And if we look back where we started with all of this, we can use it to decide that this is a better structure than this, because on this one we have no formal charge, carbon forms 4 bonds and oxygen forms 2. But on this one we would have a formal negative charge on the carbon, right, and a formal positive charge on the oxygen. And it takes energy to stretch the negative charge away from the positive charge. Overall, the charge is 0, which we would predict. But we've added energy to pull the electrons away from the protons, where here we haven't added any energy, so this is a better structure. Okay. So that's how we use formal charge.